Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So this is for the class Calculus 2 MTS 3102 for group 2. So in this course, the first chapter that we are going to learn is about the sequences. So everything about chapter 1 is about the sequences. And another thing that you should know about this course or this subject is that the information or the things that you have learned during Calculus 1 would be used in this Calculus 2. So you need to recall back what you have learned in Calculus 1. Okay, because Calculus 1 is the prerequisite for Calculus 2. Alright, so let us proceed. So in this chapter, I would give to 4 parts or 4 objectives that we need to cover. Okay, so the first one is that from this chapter, you should be able to define what is a sequence. Okay, you should know the concept of sequences, and you should know how sequences being notated, or you should know how to give the basic notation for the sequences. Okay, second part, this is regarding the limit of sequence. Okay, if you can recall on Calculus 1, you have learned on how to find the limits for function. But in this chapter or in this course, you need to know how to find the limit of a sequences. And you need to know whether that the sequence is converged or not. Okay, so you need to know how to determine if the sequence is converged or not based on the limit. Okay, the third one is you need to know how to determine if the sequence is increasing sequence or decreasing sequence. So this is also applying the things that you have learned during Calculus 1, like the way for you to know if the function is increasing or decreasing. Okay, so please recall back on that. And the last part is on how to determine if the sequence is bounded below, bounded above, and is it the sequence is fully bounded. Okay, so we will look at this one by one. Okay, so for the introduction, okay, first we need to define what is sequence first. Okay, so sequence is a set of numbers written in a definite order such that you have A1, the first term, this is the first term of the sequence, and then you have A2, the second term of the sequence, okay, A3, and so on until the nth term of the sequence. Okay, so sequence is a list of numbers that is divided by comma. Okay, and you should know that the n, or I mean like it should have A1, A2, A3, and so on until AN. And there is no such thing as A1, A1.5, A1.7, and so on, because this n should be integer number, means that it should be a positive integer. So it's just like 1, 2, 3, 4 until and so on lah, until infinity. So this n also can starts with 0. It can be A0, A0, A1, A2, and so on. Okay, so A1 is called the first term, A2 second term, and AN is the nth term. Okay, and then an infinite sequence is also denoted by this generalized notation. Okay, that is, we have the curly braces of the sequence En, such that we know that we can define that the n starts with 1 until infinity. So this one we call as infinite sequence because it goes until infinity. So for this one, that is, if you try to expand the same thing, you try to expand, it should be A1, A2, A3, and so on until I can write as the last term would be A infinity, but we don't know the exact value of the infinity. Of course, it goes nowhere, it goes forever. Okay, example 1. So let us try to do this. This is very easy. So write down the first few terms of each of the following sequences. So we have these sequences, that is n plus 1 divided by n square, and this sequence starts with the n equals to 1 and ends with n approaches to infinity. So this is easy. What you can do is just plug in the value of the n. So for example, this is the first term. Okay, the first example, which is A. We look at this solution. It is provided for you, but just you need to check and try to do it by your own. Okay, so the first term which starts with n equals to 1. So if you plug in n equals to 1 into this sequence, you would get, okay, I wrote it back here. So you would get 1 plus 1, which is 2, divided by n square, which is 1 square. So 2 divided by 1 square is just 2. So this is what you get. Okay, second term, you should get this one, that is n equals to 2. So 2 plus 1 is 3, divided by 2 square, which is 4. Okay, so that's why you get the second term is 3 over 4. The third term, which is 3 plus 1, you get 4, and then 3 square is 9. So that's why you get 4 over 9, and so on. If you try to find, just find some few terms only. Okay, so just plug in the value of n for you to expand from these notations of general sequence to this list or the expanded versions of the sequence. Okay, I know that is easy. Okay, and then we look at the second one. Okay, this one, the same thing. You can expand this general notation into the expanded version a bit by expanding on a few terms. So if you expand this one, you know this is for the case when n equals to 0. Okay, notice that for this sequence, the n starts from 0 until infinity. So when n is 0, okay, I wrote back it here lah. Okay, so negative 1 to the power of n plus 1. So means that when n is 0, negative 1 to the power of 0 plus 1, you would get negative 1 to the power of 1. That is negative 1. And you divide by 2, the denominator is 2 to the power of n. So for the case of n equals to 0, then 2 to the power of 0. So 2 to the power of 0, it is actually negative 1 divided by 2 to the power of 0 is actually negative 1 divided by 1, because 2 to the power of 0 is 1. So you just get the first term when n equals to 0 is negative 1, which is the same as what is given in the solution. Okay, second term is n equals to 1. So you just substitute 1 inside this sequence. So negative 1 to the power of n plus 1. So n here is 1, so negative 1 to the power of 1 plus 1, you get negative 1 to the power of 2. So negative 1 to the power of 2 should be just 1. Okay, and then the denominator 2 to the power of 1 is 2. Okay, so you get the second term for the case n equals to 1 is 1 over 2. So you get the same thing as what has been provided as the solution here. And you can try to check for the rest. Okay, so if you look at this these expanded versions of the sequence, you can see that it starts with a negative number, negative 1. And then second term, it is positive number 1 over 2. And the third term, when n equals to 2, you see that it is negative 1 over 4. The fourth term, when n equals to 3, you get a positive number 1 over 8. So if you look at this is actually we call as alternating sequence, because the value is alternating from negative value to positive, and then negative to positive, and so on. So we call this sequence as the alternating sequence. Okay, example C. So this example, it involved with the digit of pi. So the sequence of Bn, when n starts from 1 to infinity, where Bn, it says that it is the digit of pi, the n digit of pi. So this sequence doesn't have a specific formula, but rather it is related to the digit of pi. So each term should be the n digit of pi, and we know that pi is 3.1415 and so on. So pi is the never-ending value. Okay, so then the sequence would be depends on the number of pi lah. So the first term is 3, okay, second term is 1, third term is 4, and so on. Okay, so means that this sequence depends on the number of pi. Okay, that is the way on how you can expand the sequence. You just plug in the value of n, which is given. Okay, so how to graph the sequence? So we usually, when we plot a graph, the same thing as we plot a graph of a function, so it should involves with a coordinates. Usually for a function we have the x and y, right? So in graph we have the x and the y axis. So this is y axis, this is x axis. So the same thing as this one, for the sequence, the x point would be the value for the n. Okay, and the point for y, it will be the value for the sequence en. So it means that at the x-axis, it is the value for the n. Okay, and at the y-axis, it is the value for the sequence en. Okay, so it means that en is depending on the value of n. The same thing as y is depending on the value of x. So for instance, okay, let us graph the sequence of this one. Okay, so you know the sequence, okay, as has been said, it should have n and then en. So let's say we start with n equals to 1. Okay, so since this sequence is said that n starts with 1, so when n equals to 1, so it means that we have the coordinates of the n is 1, that means we have 1, and then en, you plug in when n is equals to 1, you get 1 plus 1 divided by 1 square, so you get 2. Okay, so this is the first coordinate for the graph of this sequence. And then when n equals to 2, the same thing, you just plug in. So you know n is 2, so this part is 2, and 2 plus 1 is 3, 3 divided by 2 square is 3 over 4. And so on, so you find out for the rest. Okay, so this has been given to you, the first few points of the graph, okay, this one. So you can try to plot this sequence. Okay, so for example, this is the graph for the first 30 terms of the sequence given above. So if you plot the points of the sequence, it looks like this. Okay, so this is the y-axis denoting the en, and this is the n lah. So this is the x-axis denoting the n. Okay, so one thing you need to recognize the graph between graph of functions and graph of a sequence. Graph of function fx, what is the difference with the graph of a sequence en? Okay, the difference between these two is that if you try to graph of a function, you know that the x can be any value, any real numbers. X can be 1, x can be 1.1, x can be 1.2, and so on, even 1.22 and so on. It just everything that is real numbers. So x is the element of real numbers. But for the case of the sequence, okay, the n should be a natural numbers, which is a positive integer. Positive integer, and it can also be 0 lah. Okay, so means that n can be the smallest possible could be 0, 1, 2, 3, 4, and so on. It should be integer. So when we try to plot, okay, when you try to plot a sequence, the graph would not be connecting from one point to the second point. Okay, so means that we just plotting the graph of the sequence just by plotting the point, but we cannot continuing the first point to the second point, because for example, this is for the case 1 to 2, right? So from 1 to 2, there is value in between, that is 1.1, 1.2, 1.3, and so on. So this value that for the that having the decimals is not the integer. So we cannot plot whatever is in between 1 and 2. So when you plot the graph, it should be no plot in between 1 and 2. It's just the plot is just on 1, on 2, 3, 4, and so on. Okay, difference from the graph of the function, you can always find what is in between 1 and 2, 2 and 3, and so on, and you would get the graph that is combined between the points. Okay, but difference for the sequence, the graph is just the plots of the point. Okay, maybe if you have a graph of a function, for this case, you might have something that is connecting. It can be connected, okay, but not for the sequence. Okay, from this graph, you would see that it starts when n equals to 1, it gives that the an is 2. And as the n is increasing its value towards, in this case, it goes towards the t, but it can happen that it goes to infinity. You would say that you would see that the sequence goes from high value to the lower value, and it eventually approaching to a certain number consistently. Okay, so in this case, what we can conclude is that this sequence would eventually approaching to a certain number when n approaches to infinity. Okay, so in this case, what does it mean is that this sequence has its limit. Okay, so in this case, I would say generally that this sequence is approaching towards 0. Okay, because it goes converging asymptotically, approaching toward 0 and so on until it goes to infinity. Okay, so we are now going to the what is the limit for the sequence. Okay, I already have learned about the limit of function, but in this part it is about the limit of sequence, but we are actually using the same idea. Okay. Okay, so working definition of limit for the sequence. So we say that the limit of sequence as n approaches to infinity is equals to a certain number L. So this L is the limit for the sequence En. Okay, so if we can make En, the sequence, as close to L as we want for all sufficiently large n. So in other words, the value of the En's approach L as n approaches to infinity. So this is just the way you translate what is being mathematically written in this form of the limit. Okay. Okay, the same thing, we say that the limit of the sequence En and approaches to infinity is equals to infinity. So the value of the En's get larger and larger without bound as n approaches to infinity. Get larger and larger means it goes to infinity lah. Okay, so the same thing likewise, limit of the sequence En as n approaches to infinity, the limit would be negative infinity. So the value of En's are negative and get larger and larger without bound as n approaches to infinity. Okay, so now the important parts from this limit is that you can recognize whether that the limit is converge or diverge. Okay, this is the things that you need to remember. So it says the first one, if limit of the sequence En exists and finite, means that you have exact value for the limit. I would say the exact value would be L, which is any number. So we say that the sequence is convergent. Okay, please remember, if you get a value for the limit, then the sequence is convergent. Okay, second one, if the limit of the sequence does not exist or is infinite. Okay, means it would be infinite, it can be negative infinity, or it doesn't exist or undefined. When you find the limit of the sequence, we say that the sequence is divergent. Okay, so if it is exists and finite, it is convergent. If it doesn't exist or undefined or it's infinite, then it is divergent. Okay, this is important. So you need to know how to determine if the sequence is a convergent sequence or it is a divergent sequence. Okay, note that sometimes we will say that the sequence diverges to infinity if the sequence, the limit of the sequence as n approaches to infinity is infinity, and if the sequence approaches to negative infinity, we will sometimes say that the sequence diverges to infinity. Okay. Okay, so how do we find the limits of sequences? So most limit of most sequences can be found using the following theorems. Okay, so let us look at this first theorem 1.1. So it says that given the sequence En, if we have the function fx, okay, such that we let for the sequence to be a function. So since this sequence is involving En, is involving with n, so we try to translate this sequence to become a function. Then we take it as fn. Okay, we make it as a function, and the limit for the function that is based on the sequence equals to L, which is a finite value. Okay, and if it happens this way, so we can also say that the limit for the sequence is also equals to L. So the idea from this sequence is that for you to know if the sequence will have a limit or not is that you can imagine, or you can let first the sequence to be a function. Okay, or maybe you don't want to confuse yourself, you can also write as fn instead of x, because you want to still use the n. Okay, but at the end of the day, just remember you have a sequence and you imagine the sequence to be a function first for you to find the limit. And then if you get the value of the limit from that limit of the function, then it apply the same for the sequence. Okay, so we go to the properties of the sequence first. So it says that if En and Bn, these two both are the sequence, two different sequence, and these two different sequences are both convergent sequences, then we can apply these 5 properties, okay, to make you easier to find the limit. Okay, this is actually the same as like the properties for you to find the limit of a function, but this is for the sequence. Okay, so let's say you have the you want to find the limit of the two different sequence, that is this is the addition lah. When you find the limit between the addition between two sequences, that is addition and subtraction. Okay, so you want to find the limit of an plus or minus with bn as n approaches to infinity. So this always can be written as this way. That is, you can always separate the first limit an and the second limit. Okay, so you can separate these two sequences into two, and it is much more easier for you to find the limit of these two. Okay, second one, this is regarding scalar, where the c, okay, where the c here is actually a constant lah. Scalar c is a constant. Okay, so when you want to find the limit of a certain constant multiply with this sequence, like this c multiply with this sequence en and approaches to infinity, you can always bring this c outside of the limit, okay, because this c is constant and it doesn't involve with any value of n, so you can bring it outside. So therefore you can find the limit by writing as c multiply with the limit of the sequence. Okay, this way. So you can just directly find what is the limit of en instead of involving the c. So it is much more easier and less complicated. Okay, the third one, this is involving multiplication between two sequence. Multiplication. Okay, but please know that this is the properties when both of these sequence are convergent. Okay, so when you have the multiplication between the two sequence a and bn, you can also separate or write the limit in a separate form. So limit an multiplied by limit bn. Okay, and then the same thing for the quotient or division. You want to find the limit of en divided by bn. So you can separate, that is the limit of an divided by limit of bn, and provided that the denominator cannot be 0 lah, or else it could be undefined. Okay, and the last one is for the case of the power. Okay, power p. So you can always bring this power p outside of the limit like this. Okay, because p doesn't involve with the limit at all. P doesn't involve with n. Okay, so that is the properties that you can use when you want to find what is the limit of sequence. Okay, next theorem. This is a squeeze theorem for sequences. Okay, squeeze theorem for sequences, if you can still remember on calculus 1. In calculus 1, you have sandwich theorem. Okay, sandwich theorem is for function. Okay, for sequence, we call as squeeze theorem. We actually apply the same idea from the sandwich theorem. Okay, so for this theorem, it says that if we have a sequence Cn that is in between of En and Bn, okay, I would say this Bn is the upper bound. Okay, because Bn is greater than Cn and greater than En, and this En is the lower bound. Okay, for all n greater than n, so know that this n is a natural number. For some n, okay, and then when we have this kind of form of the sequence, okay, and it gives you that if the limit of the lower bound En is equal to the limit of Bn, which is equals to L certain number, certain finite number, then the limit for the things that is in between the En and Bn should also be the same value, which is also L. Okay, so means that whatever is in between the limit that has the same value of a limit, then whatever is in between that is also having the same value of limit. Okay, sandwich theorem, whatever is inside should have the same things as what is in between. Okay, that is the idea. Okay, and then third theorem, theorem 1.3. So in this theorem, it says that if the limit for the absolute En equals to 0, okay, then the limit of just En is also equals to 0. So in this theorem, we can actually apply the previous squeeze theorem. Okay, so note that we can write the absolute of En is lesser equals to En and is lesser than absolute En. Okay, this is negative, this is positive lah. So this is upper bound, this is lower bound, this is what is in between. That is the general En. Okay, then you try to find what is the limit of this this lower bound, which is the limit of negative absolute En. So if you try to find this you can use the properties of the scalar. So you know this is actually -1 multiplied by absolute of En. Okay, so you can always bring this -1 outside. So what you would have is negative kat sini, right? You apply back the properties. Negative multiply with the limit, just absolute En. So based on this theorem, it says that this limit of absolute En is 0, right? So it is equals to 0. 0 is a finite number. Okay, and then we have a limit, this one. Okay, the same thing lah as what has been explained kat sini. Okay, and so by the squeeze theorem, we also must have the limit of the En is also equals to 0, because the lower bound, the limit of the lower bound is equals to the limit of the upper bound. This is the upper bound. This is upper bound. This is lower bound. Okay, so based on the squeeze theorem, when the limit of the upper and lower bound is the same, then we can say that what is in between, that is En, should also have the same value for the limit. So that's why this theorem give its a statement this way. Okay, so it becomes this one. Okay, next theorem, theorem 1.4. So the sequence r to the power of n starts with 0 to infinity, converges if the r is in between of -1 and 1 and lesser than 1. Okay, converge if the value of r is this one, and diverge for all other values of r. Okay, also that you can make it more specific. Okay, so so also it says that the limit of the sequence Rn, okay, so also it says that the limit of the sequence Rn is 0 to infinity, the limit would be 0, okay, if the r is in between -1 and 1, and the value for the limit would be 1 if the r is equals to 1. So these two case is for the case of value when r is -1 and 1 lah. Okay, so this is convergent. Okay, so this is what is given in this theorem. We will look later on how can we apply this theorem in order to recognize if the sequence is converged or diverged. Okay, to know the sequence will be converged or diverged, we need to find the limits. So I write it here. To determine convergent or divergent of sequence, we need to find the limit. Okay, and we apply okay, these two things. Okay, you can determine based on these two things. So you find the limit first, and then you decide, does the sequence is converge or diverge? Okay, so we go to example 2. So example 2, determine if the following sequences converge or diverge. So if the sequences converges, determine its limit. So means that if the sequence is converged, then it has a value for the limit. Okay, let us look at the first one, A. Okay, this is actually easy. You need to actually apply the concept that we have learned from calculus 1. Okay, so you have this sequence, 3n square minus 1 divided by 10n plus 5n square, and n you need to recognize it starts from 2 to infinity. Okay, to solve this, you want to determine converge or diverge. We need to find the limit. Okay, so we find the limit for the sequence 3n square minus 1 over 10n plus 5n square. Okay, you have this one. So to find the limit, okay, at first you might want to just directly plug in what is the value of you just want to plug in the value of n with infinity. So if you plug in the value of n with infinity, you would get 3 multiplied by infinity square minus 1 is also infinity, divided by the denominator 10 multiplied by infinity plus 5 infinity square. You should always get infinity. So this is infinity over infinity. It gives you indeterminate form. Okay, recall back calculus 1. Okay, when you have indeterminate form of solution, what you need to do, you need to adjust the sequence. You can use factoring, or you can use L'Hopital's rule. Okay, so that you would get the value that is not indeterminate form. Okay, so if you try to just directly plug in, you get indeterminate form. So that's why we factoring the highest value, which is n square, outside. Okay, so we factor n square outside, then we get n square, 3 minus 1 over n square. And for the denominator, we factor n square, we get n square multiplied by 10 over n plus 5. So we can cancel out this 2n square. Okay, when we cancel out, what we get is this form. Okay, when you get this form, you can try to plug in the value of n. So you plug in the value of n as infinity. So for 1 over n square, this one would become 1 divided by infinity. You get this one is 0. Okay, the same goes for this one. 10 divided by infinity, you get 0. So what's left is just 3 and 5. So the answer for this limit is 3 over 5. So 3 over 5 is a finite number. And it exists. Okay, finite number and it exists. So you can say that, okay, sorry, this is typo. Please correct the sequence, not equence. Okay, finite number, so means that the sequence converges and the limit is 3 over 5. So you need to always make a conclusion like this. Okay, because this is what the questions ask. So the sequence converges and the limit is 3 over 5. Okay, okay, instead of by using this factoring, starts to adjust the form, okay, you can actually try to use the L'Hopital's rule. Please recall the L'Hopital's rule. I think it is also easier. Okay, if you apply the L'Hopital's rule, means that you need to differentiate the numerator and denominator. So in this case, we have limit n approaches to infinity. So you differentiate the numerator 3n square minus 1, you would get 6n minus 1. Not 6n minus 1. You get 6n only, and differentiate 1 is 0. Okay, and then the denominator you get 10 plus 10n. Okay, so if you directly plug in the infinity here again, you would get infinity over infinity. So you get the indeterminate form, and again we can apply the L'Hopital's rule the second time. So apply it again, limit n goes to infinity. So you differentiate 6n, you get 6, and then you differentiate 10 plus 10n, you get just 10. Okay, so this gives you, the answer is 6 over 10. It can be simplified to 3 over 5. Okay, so you get the same value for the limit if you apply the L'Hopital's rule. So this depends on what kind of form of the limits lah. Okay, we go to the second example. Okay, second example is involving exponent. Okay, so in this case, it is easier to use the L'Hopital's rule. So let us define this sequence to be a function. So exponent to x over x, and note that it is actually exponent to n over n lah, because this is about sequence. So we consider n. So you take the limit of the, okay, so you take the limit for exponent to n divided by n. Okay, the same thing if you take it as a function lah. Okay, alright, so you solve this limit, okay, by using the L'Hopital's rule, because if you directly substitute the n as infinity, you would get something that is indeterminate form. You will get infinity over infinity. So you differentiate the numerator, you would get, differentiate exponent to n, you will get 2 exponent to x. Or you can also write this as in terms of n. Okay, sorry. Okay, for the L'Hopital's rule, maybe to follow its condition, we consider it to be a function lah. You can write in terms of x, but I think it is no problem if you write in terms of n as well. So we can write as 2 exponent to n divided by 1. Okay, so this is also the same as limit n goes to infinity, 2 exponent to n. Okay, so if you directly substitute infinity inside the n, you get infinity. So 2 multiplied by exponent 2 multiplied by infinity, you get 2 multiplied by infinity, you get infinity. Okay, so the answer of the limit is that the limit is infinity. So recall back the definitions how to determine the convergence or divergence. If you get the limit is infinite, in this case infinity, then the sequence can be concluded to be diverge. Okay, I think because since we use if we consider the L'Hopital's rule, L'Hopital's rule is applicable for the case of function. Okay, so that's why we consider the limit to be in the form of x. Okay, but it gives you the same answer lah, but it's just a way of writing. Okay, so in this case the sequence is diverges because the limit is infinity. Okay, next example, C. So you have sequence -1 to the power of n divided by n, and starts with 1 to infinity. Okay, so for this sequence, we can use theorem 1.3. Okay, 1.3, it's about, I think it's about, okay, the absolute thing. Okay, this is theorem 1.3. We try to apply that theorem. Okay, so to apply that theorem, since we have -1 to the power of n, so we try to find what is the limit of the absolute of the sequence. Okay, because we want to apply the theorem 1.1, 1.3. So you find the limit of the absolute of the sequence like this one. Okay, the limit should be the same as the general one, that is -1 n over n. Okay, because we want to apply 1.3 to find what is the general one, the one that you want to find, we try to find the limit for the case of the absolute. If the absolute got a certain number, then it apply the same for the general sequence. Okay, so that's why here we find the limit of the absolute of the sequence. So if we try to find the limit of the sequence, okay, how can we get the limit is 1 over n? Okay, so okay, you can think this logically. So let's say you put okay, let's say you try to expand this sequence. If you try to expand this sequence from n1 to infinity, you actually get the first term is -1 to the power of 1 is -1. -1 to the power of 2 is -1 square is 1. Okay, and then the third term is -1 to the power of 3 is -1. And it will be alternating from -1 to 1, -1 to 1, and so on. Okay, so the value could be just either -1 or 1. Okay, so okay, and then divide by n. Okay, so let's say we consider for this sequence we choose 1 lah. Okay, in this case we choose 1. So limit of 1 divided by n, and n is, we can plug in n as infinity. So 1 divided by infinity you would get 0. Okay, but the same thing also lah, if you find the limit of n goes to infinity for -1 over n, you also will get 0 lah. So -1 divided by infinity, you also get 0. So means that here the sequence converges to 0, because 0 is a finite number. Okay, so the sequence converges to 0. Okay, the last example, we have -1 to the power of n starts with 0 to infinity. So for this form, we can recall on the theorem 1.4. So because 1.4, it involves with the type of sequence that having a power. Okay, so it converges if this r is in between -1 and 1, including 1, and diverge for another value. And we have this given condition for the convergence. Okay. Okay, so using theorem 1.4, okay, so r here we recognize the r is -1. This is the r. Okay, so when r is -1, we look at back at the condition when r is -1. Okay, for the convergence part, okay, okay, so here it says that the limit of the sequence is convergent if r is in between -1 and 1, but this is not including -1, and not including 1, but rather the things that is in between the r, unless it gives you this symbol lah. Okay, so in this case, it is not false in this condition. Okay, it doesn't false within this condition, so it means that the sequence is diverges. Okay, because the r is -1, it doesn't fall in the convergence condition. Okay, so this one you apply the theorem 1.4. Okay, we look at the next theorem, theorem 1.4. Okay, okay, here we have a redundant. Okay, but sorry, this is also 1.4 kan, but it's okay. Just read this theorem as its own. Okay, so for this theorem, for the converges sequence En, okay, if both the limit of a to n and the limit of a to n plus 1 has the same value for the limit, then the sequence is convergent and the limit for the sequence is also equals to L. So this is actually it almost the same as applying the squeeze theorem. Okay, so you should know that we have the general sequence that is En, and the sequence of a to n and sequence of, okay, sorry, I write it this way, and a to n plus 1. Okay, this is actually, I would say, this is the sub of the sequence of En. So means that somehow this a to n and this a to n plus 1 is inside this part of the big sequence En. Okay, so a to n means that a to n, this is for the even terms and this is for the odd terms. Okay, because why? Because when we, let's say we start, the n starts with 1, then we have 2 multiplied by 1 is 2. So you have a2, then you have 2 multiplied by 2 is a4, a6, and so on. And for this one, it is odd because if you plug in the n, you would get a3, what else? a5, a7. Okay, but for this, the big sequence, we have a1, a2, a3, and so on. Okay, so the terms a2, a4, a6, a3, a5, a7 is actually inside the big sequence. Okay, that is the idea. So how to prove this? Okay, to mathematically prove this, it is written this way. You can try to understand. So we just follow this proof. So since limit of the a to n, this is for the even, equals to certain number L, there exists n natural number, positive natural number, such that this n is greater than n1. So we know that the difference between the sequence and the limit is lesser to a certain value epsilon. So the same thing for the another subsequence a to n plus 1. This is for the odd. Okay, there is n2 greater than 0 such that this small n is actually greater than the natural number n2. So we know that the distance between the sequence and the limit is less to certain value of epsilon. So it applies the same thing. So let n the natural number, the maximum for 2n1 and 2n2 plus 1, and let n is greater than this natural number. So then either an is equals to a to k for some k greater than n1, or this the big sequence en is equals to a to k plus 1 for some k greater than n2. And so in either case, we also have that the en, the distance between en and L, is also less to epsilon. So the same thing apply lah. Okay, so we can say that the limit of the big sequence En or general sequence En is also approaching to L. The limit is also the same as the odd subsequence, and this is even subsequent and the odd subsequence. And so An is also convergence because it goes to the limit, a finite value of the limit. Okay, so An is also convergence. Okay, that is theorem 1.4.